Hi students, and welcome to lecture 10 of the LN 2016A Electronics 1 course. I'm your lecturer today, Mohammed Dango, and we'll be looking at the voltage regulator. Starting off, we're going to have a quick recap on the power supply. We're then going to look at the regulator integrated circuit. Then we're going to move on to the Zener diode characteristics, the Zener regulator circuit, and finally we're going to design a Zener regulator circuit. Now, if you need to check your textbook, chapter 2, pages 85 to 90, and always remember anything said or done in this lecture can and will probably be used as a question in the test or the exam. Recap, students, the power supply, as we know, it has four components. The transformer, which has a normal transformer, schematic shown here, or a center tap transformer, which divides the secondary coil into two different voltages. Moving on, we have the half wave or the full wave rectifier. I took you through the three different types, which was half wave, center tapped full wave, and the bridge full wave rectifier circuits. After that, we had the capacitor filter, and of course you remember from a capacitor filter, it simply operates in two steps, which is the charging and the discharging. And finally, in today's lecture, students, we're going to be looking at the voltage regulator. The purpose of the voltage regulator is to take this capacitor filter output and smooth it out into this very nice straight DC line. And yes, in today's circuit, we'll be looking at the regulator IC, and this is the schematic of our regulator IC. And then we'll be looking at the Zener regulator circuit, which has a Zener diode. And the first thing that we want to know, students, is where exactly do we connect this regulator IC in the three different configurations of rectifier circuits shown here: half wave bridge, center tapped full wave, and full wave bridge rectifier circuit. And we can see that after our capacitor filter, we simply connect our regulator, and after our regulator we then have our load resistor, which will have that very nice V out DC across it. Now, looking at the regulator IC schematic, students, we see that it has three pin outs, the first being the input voltage, second being ground, and the third being the regulated DC output voltage. And when you get a regulator IC, students, it has a label which is either 78XX or 79XX. Now, the 78 regulators are all positive voltage regulators, and the XX can be 05, 09, 12, and so on. And that simply is the voltage output. So the 7805 is a positive voltage regulator that outputs 5 volts. And the negative regulators, well, they defined or labeled with 79. And once again, 05, 09, 12, that simply means the voltage output. So the 7905 will output a negative 5 volts. And students, when you're building a circuit that has a regulator in it or a regulator IC, always make sure to put some ceramic capacitors between the pins. The first ceramic capacitor goes between pin 1 and 2, which is V in and ground. And the purpose of this pin is to get rid of any AC noise that might be on this voltage input. The second ceramic capacitor gets put between pin 3 and 2, which is the output and ground. And the purpose of this ceramic capacitor is to filter out any high frequency noise that we might find on the output signal. Now, students, we all know that the purpose of our regulator IC is to maintain a fixed or constant DC output voltage at the V out and ground terminals. But we know that when we connect it to our capacitor filter, at our V in and our ground terminal, the voltage regulator is going to experience some line fluctuations. And these line fluctuations are caused due to the capacitor filter output, which is shown here on this red curve. And we can see that that is due to this V ripple peak to peak. Now, when a regulator circuit is connected to the filter output, these variations will still be there, but it is possible that also on the AC input to our transformer, we'll also see some of these fluctuations, and the regulator circuit is going to get rid of them, and it's going to maintain a constant output DC voltage regardless of the fluctuation that it's subjected to at its input terminals. Now, on top of our line fluctuations, it's also important for us to consider the percentage line regulation and the percentage load regulation of our DC power supply. Now, students, the percentage line regulation is simply defined as the ability of a DC power supply to maintain a constant output voltage as well as a constant output current to supply the load despite any changes to the input voltage. And we can calculate that by simply saying the change in the output voltage divided by the change in the input voltage multiplied by 100%. Next up, the percentage load regulation, and this is the ability of our DC power supply to maintain some specific constant output voltage despite any changes in the amount of current that is drawn. And we can calculate our percentage load regulation by taking the no load voltage minus the full load voltage divided by the full load voltage multiplied by 100%. Now you're probably wondering at this time, what the hell is full load voltage and no load voltage? Well, students, the no load voltage, as you see on this plot over here, that is simply the voltage that we see when no current is being drawn from our DC power supply. So in other words, we have a resistor or a load which has an infinite value, so an open circuit, and we measure the output voltage of our power supply, and that is our no load voltage. Now similarly, the full load voltage is the output voltage when the maximum possible current that our power supply can supply is drawn from it. So the load resistance that we see being connected to our power supply is very small, and it is drawing this maximum current that we see. And the output that we see at that specific resistor or load is known as the full load voltage. Now, a good regulator or a well-designed power supply has a very small percentage regulation, which means that the difference between our no load and our full load is going to be minimized. And finally, students, the last thing that I need to tell you about your regulator IC regarding the pins is always be sure to consult or check your manufacturer's data sheet to make sure that they are in fact pin 1 being V in, pin 2 being ground, and pin 3 being V out. I know I messed this up when I was in my master's year. We were building some PC boards for a flyback converter, and I assumed that, like all regulators, V in was pin 1, ground was pin 2, and V out was pin 3. And that's what I went with for my schematic design. And it turns out that the input and the output pins were switched on this specific Chinese regulator. Go figure. And that messed up quite a few boards that we had, which we had to completely rebuild. So always make sure to check your manufacturer's data sheet to make sure that the pins are what they say they are. Moving on, students. Now here's something that I think we're all familiar with, the Zener diode characteristic curve. Now, of course, we can see from our Zener diode characteristic curve, the blue part is the forward bias region, the purple part is the saturation, and the red is the breakdown region, which is obviously exactly where we want to be operating our Zener diode. Now, students, there's a bit more detail in this breakdown region that we can't really see from this characteristic curve. So what I'm going to do in the next slide is I'm basically going to zoom in to this curve so we can see all the intricate details that are going on around here at this breakdown point. Aha, and there we have it. So when we zoom into our curve, we now see that our Zener diode actually has a certain minimum Zener voltage and a maximum Zener voltage that it can operate at. And at our minimum Zener voltage, we see some minimum Zener current, and at our maximum Zener voltage, we see some maximum Zener current. Now, it's important to note, students, that the difference between our minimum and maximum Zener voltages is very small, because remember, our Zener diode tries to regulate whatever voltage it is across it at the breakdown point. So this difference between the max Zener voltage and min Zener voltage is obviously going to be very small. However, the difference between the minimum current and the maximum current, well, that's going to be a bit larger because we want our Zener voltage, our Zener diode, to pass quite a bit of saturation current so that it can act as a type of a regulator. And we can also note, students, that because this curve in the breakdown region has a slope, we know that that means it's going to have some sort of a resistance. And next up, students, I want to just show you how we go about modeling our Zener diode according to the different characteristic curves that we see. So for the forward bias characteristic, we know that a Zener diode behaves similarly or exactly as a small signal or a rectifier diode. So when we are forward biased, we simply replace our Zener diode with a DC voltage source. And if we want to take into account the resistance or the diode resistance, then we put this resistor RD in series with that source. When we are operating our Zener diode in the saturation region over here, we know that it is non-conducting, so we simply replace it with an open circuit. And then finally, students, when we are operating our Zener diode in the breakdown region, which is exactly where you want to be operating it, we replace it with a Zener diode source. Now notice that the Zener diode source compared to the diode on source have opposing polarities according to the anode and the cathode of our Zener diode. So the positive terminal of this battery is at the cathode of our Zener diode, whereas the positive terminal of this battery is at the anode of our Zener diode. And that's how we can distinguish between reverse bias and forward bias. Now, of course, I mentioned that because there's a slope in the reverse bias curve, there's some sort of a resistance that we're going to encounter. And students, we know that every single circuit element, from your battery to your wires, to your resistors, to your cables, they all have some resistance. So if we want to take into account our Zener resistance when we are reverse biasing it, we simply put a resistor in series with our Zener source, and that resistor has a value of RZ. And now that we're familiar with the various models of our Zener diode and the characteristic curve, let's move on to the Zener regulator circuit. On this slide, students, we have the Zener regulator circuit. Now at this point, I want you to just take it all in, because for the remainder of this lecture, we're basically going to be analyzing the hell out of the circuit. So looking at the circuit, we have a variable input voltage, which is a DC voltage. So that has an input voltage which has some minimum value and some maximum value. On the second part of the circuit, we have a resistor RS, and we then have our Zener diode, which is connected in parallel with the third part of the circuit, which is a variable load resistor. So that means this load resistor is going to draw a current, IL, which is going to have some IL minimum value and some IL maximum value. So let's go ahead and begin analyzing the circuit. The first step to analyzing the Zener regulator circuit, students, is to assume that our Zener diode is switched off. And that means that we haven't yet have a voltage at this terminal that is less than our Zener voltage. So that's how we define this here. So we know that our input voltage minimum minus the voltage dropped across our resistor RS is less than whatever our Zener diode voltage breakdown needs to be. So we don't have this Zener diode being broken down, therefore we know we replace it with an open circuit, and of course it's not being forward biased because the anode is not connected to this voltage being applied here. The anode is connected to ground. Now don't think that no current is going to flow in the circuit because of this open circuit, because our load resistor is still connected in series with resistor RS and our voltage source. So our load resistor and RS are still going to pull a current IL. And we can determine that current with some good old-fashioned KVL. So from KVL, we can determine IL is equal to Vin divided by RL plus RS. And now that we have our current IL, we can determine our output voltage, Vout, is simply Vin over RL plus RS multiplied by RL. And we know that this is simply a voltage divider. Aha. Now next, students, if we look at what is called the no load circuit, so we throw out this load resistor completely and we take our multimeter and we measure what is the voltage between these two terminals, we'll simply see that our output voltage is equal to our input voltage for our no load circuit. After off comes on. So here we have the on case where our Zener diode is reverse biased and it is operating in the breakdown region. So we replace it with a source that has a voltage equal to the Zener voltage, which is the breakdown voltage of this Zener diode. So because we have Zener on, we know that whatever this input minimum of our input is, minus the voltage dropped across the resistor Rs, is still going to be greater than or equal to our Zener voltage VZN. Now let's say you have a 5-volt Zener diode. That means that this voltage on the left-hand side of the expression needs to be 5 volts or more. So now, students, we can perform a KVL in this loop over here so that we can determine this current Is, which is going to be supplied by our source or our input. So Is is simply Vin minus Vz, because we have Vin on this node and we have Vz on this node, on this side of the resistor. So Vin minus Vz divided by the resistor value Rs. That's how we get Is, or the current that is now being supplied through the circuit. Now then, students, we can perform the other one of Kirchhoff's laws, and I think this is the first time ever in my lectures that we are applying good old-fashioned KCL, or Kirchhoff's current law. So we know that all current that comes to a specific node is going to divide equally, and you can then sum them back up. That is Kirchhoff's current law. So if we look at the direction in which the currents are flowing, from KCL we can determine that Is, which is coming here, flows to the KCL node, is equal to Iz plus IL. Aha. So that's what we can get from KCL, and then finally we can determine what is the output voltage that we're going to see across our load resistor. Well, students, that's a very simple one. We know that this Zener diode is acting as a regulator, which means it's going to maintain a constant voltage across our load resistor. And that's why we connect it in parallel with our load resistor, because two components that are connected in parallel have the same voltage across them. However, as we can see, the current that flows to them is different. So we can note that the output voltage, or the voltage at this big node over here, is simply going to be our Zener diode voltage VZN. Now that we've seen how our Zener regulator circuit can operate with either our Zener diode being off, so it's an open circuit, or it being on, so it's replaced by the source which has the Zener breakdown voltage, we can move on to actually designing one of these bad boys. Now, students, anytime you design any circuit, there are certain things that you are going to know. And you know these things because you, as the engineer designing it, have to specify them to move forward with your design. So first thing in our Zener regulator circuit design that you know because you specify it is your input voltage characteristic. And that is this source over here. So your input voltage characteristic Vin, you know what it is, and you can actually set the source to whatever you need it to be, Vin min or Vin max. But sometimes, students, it might be a constant input that you see, and that's why I've said here it can be constant. Next up, students, you're going to know what is your required regulated output. This is a definite need to know, because let's say you have a circuit component, for example, an LED screen, and this LED screen needs a 5-volt DC input. So then you know that your required regulated output from your power supply has to be 5-volt DC for this LED screen. So that's how you know what your output voltage is and how you specify it. Next up, students, because you know what your output voltage is, that makes it very easy for you to choose your Zener diode. So continuing with the example, you need a 5-volt Zener diode. So that is our VZN, which is the breakdown voltage of our Zener diode. We now know that that is 5 volts out because we need 5 volts out to power our LED screen. Also, once you specify your Zener diode or you choose it, you can then look at the data sheet for the two currents. Iz min being the minimum current that needs to flow into the Zener diode to make sure it is actually reverse biased, and Iz max, which is the maximum current that is allowed to flow through the Zener diode, because if you exceed Iz max, you will blow up your Zener diode, and then of course the best place to put it is the bin. And of course, if you go below Iz min, you won't reverse bias this Zener diode, and you're going to see an open circuit here, and you're going to have a very unregulated voltage output on whatever load it is. And if it's your LED screen, chances are you're going to then damage it. So very important to know what Iz min and Iz max is. But sometimes on these Chinese data sheets, we find that they don't give you IZ min and IZ max, they give you power max of your diode. But we can take our power max and simply divide it by our VZN to calculate what is our IZ max. And then for our IZ min, which is step 4, we can simply assume what that is by taking 10% of IZ max. So that's how we specify all our Zener parameters. And then finally, students, you know what your load characteristic is. As I said, you know that you need to power some LED screen, so you know what the characteristic of that LED screen is, so you know what your load characteristic is. Now, sometimes you might have a constant load characteristic. That's also okay. Now, based on what I've shown you and the stuff that you know, there's only one thing in the circuit that we don't know. And the thing that we don't know is this pretty little resistor over here, RS. And for the next few slides, we're actually going to go into figuring out how do we specify what RS needs to be based on what we know. And the first step towards trying to figure out what the hell RS needs to be is to try and determine what is the magnitude of this series resistor. So to proceed with determining this, we need to assume that our Zener diode is in fact in breakdown, and that is a very good or valid assumption because that's exactly how we want the circuit to operate. We want our Zener diode to be in breakdown to maintain a constant voltage across our load resistor. So that's a good assumption. So this is the equivalent circuit that we're looking at, and in this circuit that we have, we know that we can have the following taking place at any time. We can have our input voltage varying between the minimum and the maximum, which will have our source or the series resistor current varying between some minimum and maximum. And of course, the Zener current and the load current are also going to be varying between some minimum and maximum values. Now, considering that we're going to be varying between all these different values, let's look at the various scenarios that we're going to find in the circuit. So here we have the different currents. The IS, which is going through the series resistor, IL, which is the current going through our load, and IZ, which is the current which is going through our Zener diode. And then, of course, we have different scenarios. So the first one, where we have a minimum current going through our series resistor, and a minimum current going through our load, and a minimum current going through our diode, well, that's okay, students. That's not going to be any issues to face with. You can then go through the other ones that are okay. Let's look at ones that are impossible. So if we have some minimum current coming out of our source and through our series resistor, can we have a maximum current flowing through our load and a maximum current flowing through our Zener diode? No, I don't think so, students. That is something that's going to be quite impossible. And then, students, we have some scenarios which are possible but not okay, or rather we can think of these as worst case scenarios. And the first one being when we have some minimum current flowing out of our source through our series resistor, it then goes through a maximum current through our load resistor, which means that whatever load resistor someone has put here is very small. That's why a small resistance is going to draw a very big current. And because we have a very big current going through our load, we're going to see a very small current, or IZ min, going through our diode. Now, as we said, students, when we have this minimum current going through our diode, if it happens to go less than this minimum current, our diode is going to switch off, and we're going to have an unregulated voltage across our load, which can cause some harm to our circuit. So that's why this scenario, although it is possible, it's not okay, because there's a chance that your IZ min is going to drop too low and switch off this diode. And then next up, students, in our not okay scenarios, is we have some maximum current IS flowing through our series resistor, followed by a minimum current flowing through our load resistor. Now, of course, a minimum current is going to flow through our load resistor if some fool decides to put a very big load at the output of our Zener regulator circuit. So if we have a very big load or big resistor that's put here, it's going to impede the current flow, so current's not going to want to flow here. And then basically we see Iz max, yes. So because the current's not really going to flow through this big load, it's all going to shunt down through our Zener diode. And of course we know that if we exceed Iz max, yeah, put the Zener diode into the bin. So that is why this second scenario, although it is possible, it is a worst case scenario because there is a very good chance that you're going to exceed Iz max and blow up your diode. But students, if we dig deeper into these two scenarios, which are worst case or not okay, we can actually use them to determine what parameter or magnitude we have to set our RS series resistor to, so that we can ensure that whatever RS's value is set to, it will make sure that we never find ourselves going below Iz min or going above Iz max. And that, students, is how we're going to actually try and determine, or rather we are going to determine, the magnitude of the series resistor RS. Okay, students, so the first scenario that we're going to look at that is not okay is when we have a minimum current flowing through our series resistor and a very big or maximum current flowing through our load, because yeah, whoever built the circuit put a very small load here. Maybe even they decided to short circuit it. So because there's such a small load, we're going to see maximum current flowing through this load resistor. And of course, that means that we're going to have a minimum current flowing through our Zener diode. And we want to analyze this to make sure that this Zener diode minimum current is not less than this, so that we don't switch off our Zener diode. So we're going to analyze this to figure out what maximum value we need to have for RS, our series resistor, because the maximum value of a series resistor is going to draw the minimum series resistor current. All right, so because we're dealing with our series minimum current, that means our input voltage is also going to be at a minimum, because we are drawing minimum power out of our input voltage source. Then we go ahead and perform a KCL, Kirchhoff's good old-fashioned current law, at this node over here, which gives us Iz min plus IL max is equal to Is min. Now we also know, students, that because Is min is going through this resistor Rs, we can use a simple, what is the volt drop across Rs? Well, it's V in min. There we have V in min on this side, minus Vz, because we have Vz here at the output. And according to Ohm's law, if we divide that by Rs max, remember I said we have a maximum series resistor value, because the maximum series resistor value will draw the minimum series current. So Rs max, Ohm's law, we now have an expression for Is min, and we also have our KCL expression for Is min. So we rearrange this second expression to make Rs max the subject, and then we can substitute our KCL expression for Is min in the denominator to get this very beautiful expression for Rs max. So that is the specific maximum resistance magnitude that you can have for this series resistor. And we know that if Rs happens to exceed Rs max, then our Zener diode will switch off, because this minimum current that flows through the Zener diode will be less than the minimum current, and it won't reverse bias it. And now, students, the next not okay scenario that we need to analyze is going to be done so that we can actually figure out what is the minimum value that this RS resistor needs to have, or the minimum magnitude that it needs to have. So in this scenario, we see that we have a maximum current. Is max is being delivered from our source. Now, obviously, if we have Is max, then this resistor Rs is going to be Rs min. So we're going to be looking at Rs min. Then, of course, looking at our load, we have a minimum current going through our load. And of course, if we have very little current going through our load, that means that some fool put a very big resistor here, or a very big load over here. And big loads, they don't attract a lot of current, which means that all the current is basically going to flow through our Zener diode. and our Zener diode is going to experience Iz max. And we need to make sure that whatever value Rs min is good enough to prevent Iz max being too big or going over Iz max, and that will cause our diode to get destroyed. So let's figure out what Rs min needs to be. So again, because we're drawing a maximum power from our source, we have V in max and Is max. Going to some good old-fashioned KCL, we can get this expression for Is max. And then again, students, we just figure out what is the volt drop across our resistor Rs, which is simply V in max, because that's the voltage on this side, minus Vz, because that's the voltage on this side. It's caused by our Zener diode, Vz. And because of Ohm's law, we divide it by Rs min. Yes, Rs min, because we're drawing maximum current from our source. So we have a very small resistor to draw maximum current. We then have this expression for Is max. Rearrange the second expression for Is max to get Rs min, the subject, and then substitute our KCL expression into the denominator to eventually arrive at this beautiful expression for Rs min. So now we have an expression for Rs min, and we know that if Rs happens to go less than this Rs min value, oh boy, our Zener diode is dead. After establishing these two magnitude expressions for Rs, another thing that we need to take into consideration, students, is the resistor power rating. So let's say we remove, or rather we put a resistor in place of Rs, and this resistor that we've put here is called Ra. Okay, don't get confused with Ra, Rs. So Ra is basically a resistor that we are putting into the circuit, and we know that the magnitude of Ra needs to meet these conditions. So the magnitude of Ra needs to be greater than or equal to Rs min and less than or equal to Rs max. So now we know exactly what the magnitude is, but we don't know exactly what the power of this resistor needs to be. So let's try and figure that out. So the resistor power rating, we know power is I squared R. And we know that the maximum power that will be dissipated across this resistor will take place when Is max is flowing through it. So because of that, we know that Is max can be expressed according to the volt drop across our resistor, and we can use Ohm's law to then divide by Ra to get this expression. And then we can use this expression and plug it all the way back into this power expression, so we can now determine exactly what this maximum power is that is going to be experienced by our resistor Ra. And we need to ensure that when we choose Ra, that the power rating of Ra is greater than or equal to whatever this power max is that Ra is going to encounter. So to recap, students, we've determined exactly what the magnitude is of the resistor that needs to be placed here in series. And after we've determined that magnitude, which sits between Rs min and Rs max, we need to ensure that the power rating of that resistor is greater than or equal to whatever maximum power that resistor is going to have to dissipate. And of course, maximum power is dissipated when the maximum current flows through it, which is Is max. Students, I know you're probably tired, but please stay with me. This is the final slide. So the previous slides, when we analyzed the circuit to determine Rs min and Rs max, we had a variable voltage source and a variable load. But what happens if we now have a constant voltage source, or if we have a constant load? So these are two other circuit or cases that we can see for our Zener regulator circuit. We can also have a constant voltage source and a constant load. So the expressions for Rs min and Rs max, well, they change slightly in this case. As you can see from this slide, Rs min and Rs max, because our voltage source is constant, we don't have some minimum or maximum value. We simply have V in our numerator. And because our a load is constant in the circuit, we then, in our denominator, we don't have some minimum or maximum load value, we just have a constant load value, which is IL. And that, students, is Zener regulator circuit design done and dusted. And a quick recap, students, we looked at the power supply, and this was the last time that you're going to see it, I swear. We now know every single component that goes into our power supply, from the transformer to the rectifier to the capacitor filter, and yes, today, the regulator. We looked at the regulator IC, and we saw that it has some line fluctuations, and we know that we need to look at the line regulations and the load regulations for our regulator IC. And of course, make sure that we know what our pins are, so you don't end up like me and building a circuit that has the wrong pin outs. We then looked at our Zener diode characteristic curve. We zoomed into that curve so we could see some minimum and maximum Zener diode voltages and some minimum and maximum Zener diode currents. We then looked at the Zener regulator circuit, which is a very nice circuit that you can build to regulate an output voltage. And we then looked into actually how do we design that circuit. And we saw that the only damn thing that we don't know in the circuit is that series resistor value. So we went through this analysis to try and determine what that maximum resistor value needs to be, or the minimum resistor value needs to be, to specify the magnitude. And then finally, we looked at what the power rating of that resistor needed to be. Okay, students, if you're still uncomfortable with anything that we went through in this lecture, please go to your textbook, chapter 2, pages 85 to 90. And of course, as always, I appreciate any comments, concerns, feedbacks. If there's an error, please let me know, students. I appreciate your time and thank you. One last thing, students, just to celebrate us coming to the end of our power supply lectures. Here's a picture of one of my 9 cats that I own. This one in question, her name is Duchess. And if we do a quick loaf check, yes, of course, no paws sticking out. I don't see any tail. Aha, that is a 10 out of 10 loaf that we see here. All right, students, I'll see you in the lecture enrichment session. Cheers.